Welcome to the case study of EMC's Durham Data Center with Ray Gonzalez and Joe Terminu.
Thank you. Good morning. How's everyone doing today? All right. Good start of the morning. My name is Ray Gonzalez. I manage data center operations for EMC's new private cloud data center located in Durham, North Carolina. I brought along Joe Terminu, who is my senior data center analyst. I guess starting off, opening a new efficient data center, a lot of hard work. It's fun, it's exciting, but there's also challenges involved with, moving into a brand new facility. We want to talk to a little bit about what we've taken on from an efficiency standpoint. The agenda today, at a high level, I want to spend a few minutes going over our data center strategy, speak a little bit about specifically the Durham data center, and then with commissioning of any new data center, you're going to have the migration. So I want to spend a few minutes on how we migrated 6 petabytes of information from Westboro, Massachusetts, down 600 miles to North Carolina. Then we'll get a little bit deeper. We'll get into data center efficiency. Joe will take you through PUE analysis, some of the great things he's been doing there. We'll review CFD modeling in an effort to improve our efficiencies. And then we'll go into cold out containment solutions that we've deployed in Durham. And then lastly, we'll finish up with really what are we looking at for future efficiencies. The Green Grid and the DCMM model have directly or indirectly had a huge influence on what we've done over the last couple of years and really what we're looking for into the future over the next 2 years. So this is our global strategy. We have 4 data centers located throughout the globe. This year in 2012, we just recently decommissioned our Westboro data center. It was our oldest facility. It was about 30 years old, and the lease was coming up in 2012, so we decided to move out of Westboro and open up a new data center in Durham, North Carolina. So today, our 2 enterprise data centers are located in Hopkinton and Durham. We have 2 regional data centers, one supporting West Coast right down the road on Great America Parkway here in Santa Clara, and then supporting EMEA and Asia Pac, we have a Cork, Ireland data center. And then lastly, we've added 2 bunkers close to Hopkinton and Durham data centers to help us with replication, business continuity, and as part of our migration, they played a big part in that. All right, so a little bit about the Durham facility. We bought the land in 2009 and we started building the data center in early 2010. I think it was February 2010. Within 9 months, we were moving into the data center. So it was a very elevated time frame, very quick. So we had to move really quick and really fast. The data center itself, the building itself is a 450,000 square foot data center. A building. And basically what EMC did is, it was an old manufacturing warehouse. So we essentially bought the 4 walls. Being that it was a warehouse, there wasn't a lot of demolition to do. So it was really quick for us to come in, get the facility prepped so we could move in within 9 months. The data center is 20,000 square feet. It actually sits right about the center of the building itself. And we can expand that building, or the data center, out to 30,000 square feet. This facility is primarily our DR site for EMC's mission critical applications. So today we're at year 2 in the building. The mix is about 85% DR, 15% primary running out of Durham. But what we expect to happen is over the next few years, as new applications, new requirements come up, we expect that mix to get down to about 50-50. And then one of our key requirements for the building was to support zero data loss business continuity. I'll get into that a little bit, but this is where the bunkers really played a huge part in our strategy. A little bit about the sustainability features of the building. The building was designed at a 1.3 PUE. Obviously, day 1, year 1, we didn't hit that initially, and caused a little bit of alarms. Joe will take you through exactly how we looked at the PUE and how we devised a plan to really drive that down and get closer to a 1.3 PUE. It was designed as a LEED silver, We just got news last Friday that certification came through, and we actually accomplished gold certification. So real big win for us. We were real excited last week. Inside the facility, we do harvest rainwater. The thought there was that with the rain harvesting solution we had in place, we would be able to reduce our dependency on municipal water by about 40%. And to date, we've saved about 2 million gallons of water just over the last 2 years. We deployed a free air cooling, so we have outside air economization. We supply the data center with 72-degree air, so roughly we can run on free air cooling 57% of the year. Supporting the data center, we have no batteries. We've deployed Flywheel UPS technology. It's been running for 2 years, been running great. We've seen a lot of great benefits from the flywheels. We have typical hot and cold aisles, just like you would. It's pretty common nowadays, and I'll go through that a little bit in some later slides. And then the building itself was really built as a flexible design. You heard Dean talk about it yesterday. And the lifespan of the building was built for 30 years. So we built triggers in place where we could quickly scale out our generators, our UPS, our air handlers, to really extend the life of the data center for 30 years. Now, inside the data center itself, we've had a lot of challenges over the last 10 years, and it's very, very common. Disparate systems inside your data center, purpose-built environments. And what we saw, 5-6 years ago was that we had a lot of these resource pools that had horrible utilizations, and we just couldn't share the resources between different applications. So that was our primary challenge from an IT perspective inside the data center. We wanted to build something that was easy, something that we could repeat in any one of our data centers rather quickly. We started designing this data center 3 years ago, maybe 3.5 years ago. So at the time, we knew that converged infrastructure was coming up. We wanted to make sure that we standardized, and we tiered our applications and our infrastructure along mission critical, business supporting tiers. And we've done I'll show you a few slides of the difference between Westboro and Durham Data Center and what we've actually achieved by doing that. We have a flexible data center design, so the cable plant, it all runs overhead, so it's easy to add, to remove cables. From a power perspective, we can go from 100 watts a square foot, where we are today, up to 120, possibly even up to 150 watts a square foot. Modular design where we can move racks, we can add cold aisle containment solutions very easily within the data center. The picture here is of one of our first cold aisle containment units. Today, we started with 2. Today we have 10 out of the 18 cold aisles contained. And then we wanted to have the capability to quickly scale out our IT infrastructure. So a lot of work was put into the first year of building that base infrastructure. Ensuring that the cable plant, our 10 gig, was run throughout the data center. Ensuring that our network chassis, our compute chassis, and our storage arrays had enough capacity that we could quickly scale out. So we front-loaded a lot of that work in the beginning. Now, as we scale to support the increasing demand, it's really just a matter of my data center operations team going and adding some new blades, adding some new DAEs, some new network switches. It happens very, very fast and very quickly. And another key item of the data center is it's 100% virtualized. Something that we've never done before, so we take great pride in showing that number. When I talk about 100% virtualization, of course I'm talking about x86-based applications. We still have some storage devices and network devices that need to run in native mode, but everything that's x86-based is virtualized. We run on a single operating system, so whether you're looking for Microsoft OS, Linux OS, it's all built on top of that virtualization layer. All right. So of course, like I said, with any new commissioning of a data center, you're going to have a migration. I mentioned that building the data center, building all this new equipment, it's fun, it's exciting. The migrations, not so much. A lot of work was put into understanding what was in our data center. As we've climbed the virtualization, as we've grown in virtualization, what we realized is we started to lose track of our applications and where those applications were sitting. So we spent thousands of man hours just trying to get a good handle of what we had in Westboro. This is what the migration looked like. It was actually probably the biggest project IT has done, EMC IT has done in the last 10 years. It's 350 applications, 2,000 virtual machines, and 6 petabytes of data. When you look at the applications, this is how they split up. So I talked a little bit about that tiering. 54% of those applications were on that mission critical tier, sitting on our highest availability platform. And then we dropped down 84 into business critical tier, and then which you should have most of your business important applications sitting on that lower tier platform. Great thing we did here is we migrated everything over the network. So without getting into product descriptions, we leveraged our own products to migrate this information over the network. And how we did it was through the use of our bunkers that I mentioned earlier. So if you have Hopkinton and Durham 600 miles apart, we created bunker strategy, right? So inside the bunker, we basically have a swing array. On that swing array, it helped us copy data from Westboro to the bunker in a synchronous fashion. So everything that was being copied and created in Westboro was also being copied in our bunker on the swing array. Then we could take that information and asynchronously move it down to Durham. When we did that, we were able to isolate this environment, test it, monitor it, make sure performance was set. Any dependencies that we may have forgotten about, we were able to ensure that once that data got to the new infrastructure, it was ready for the migration. Then before we actually did the final migration, we took one last snapshot, sent it over to the swing array, shut down the primary app. Once that data was moved down to Durham, then we were able to follow that same checklist to make sure we test it, we monitor it, performance is good, dependencies are checked off. We could quickly just flip the switch and move that application down to Durham. So when we did this, we did it with very, very little downtime to the business. I'm not going to lie and say that everything went well. There were some migrations that you only know what you know. So some migrations we had to scale back, but it was a very, very small percentage. But the overall downtime to the business the impact was really, really small. And the great thing about it is you get to test the environment before you switch over. All right, so here's some of the benefits that we realized. We really wanted to focus in on the servers, the storage, and the power. I have quite a few slides, but I thought this one was the best. When you look at the hardware and the capacity, we were able to increase our capacity, but lower our power demand. So from a server perspective, we increased our capacity by 67%. Virtualization, of course, went up about 200%, given that Durham is 100% virtual. But the interesting point here is that our watts per server actually went down, and it went down by a lot, went down by about 74%. Same thing happened on the storage side. So storage actually grew 138, almost 140% in capacity, and we reduced our watts per terabyte by a whopping 82%. And then now if you look at the actual facility and the power from the facility, this is interesting because if you look at the IT load, yeah, we went down about 33%, but the total load from IT equipment and the facility equipment went down 56%. So in Westboro, we were looking at 2.4 megawatts between IT load and the facility load. We were actually able to cut out about 1 megawatt, and a lot of that came from the efficient facility infrastructure that we put in place in Durham. So all good numbers and all where we expected this to go. All right, so that's a little overview of the strategy. Now, what I mentioned around data center efficiency, moving into a new data center, we didn't see what we expected. We moved into this highly efficient data center, and we realized that day one and year one, we weren't as efficient as we expected. So Joe ran a lot of projects around understanding our PUE, understanding what were all the nuances and how the calculations of the PUE, and how we could really drive the efficiencies of the PUE.
Thanks, Ray. So just the layout of the data center itself. As Ray mentioned, we built out the data center in 9 months. The design for that actually took about 3 months. We had an architecture firm run a little over 50 different CFD models to figure out what was going to be the most efficient way for us to get as much power into this room as possible. Okay. So the design goals, as he mentioned, was 1.3 PUE. So the first question that we went back to the architect with was, okay, so we're supposed to hit 1.3, but when can we actually expect to achieve that? So the numbers they came back with was we should be able to achieve 1.3 when we get to a 1.5 megawatt IT load. And that would only happen when we were in ESS mode on our UPS system and during free cooling. Okay, so once I had that information, I could put together a chart, which I'm showing here, which basically, assuming our mechanical overhead stays relatively constant, which it should, because the system was front-end loaded. So we've got 100% UPS. Everything's already in place for that 20,000 square feet. So this was the chart that really just kind of shows what we should expect as we start migrating our gear down into Durham. As the IT load grows, our PUE is going to come down. So how did we benchmark across that? Now that we've been in there about 2 years, we've just crossed about the 800 kW threshold, and you can see that we've actually trended very well against the design. We've been able to follow that trend and even make a number of improvements along the way. You see some good dips in there. So from a validity standpoint, the design held up, and we've been able to track very closely to what they had predicted that we should be able to achieve. So one of the things that we very quickly realized when we commissioned the new building is just how much data there is available to us. It has all the latest technology. The building's completely automated. There's literally over 60,000 points that the facilities organization collects data on to manage that building. Plenty of data for us to look at. Not the most easy interface to find the data that you need. So what we did was we spent a quarter and we developed a little piece of software that we call our data center widget. And this widget is a real-time interface. It goes out and gets just the data points that we want to be able to look at every 15 minutes. So we have a dashboard. If you look at the screen on the right, that just floats on all of our desktops and operations, and we can see our PUE, our mechanical, or ITKW, temperatures, humidity, dew point, air handler economization status, or even total CFM. So having that data instantly available to you without having to send your entire staff to training on the BMS system was a nice win for us, because now we can actually see everything that's going on in the data center. Second piece to that is the data center dashboard, and that's just an extension of that data set. But now what we can do is we can actually take the data and trend that during any time period that we want. So any of those 10 different data points that we want to look at, we can quickly get access to a graph going back to day one of the facility and start looking for any issues or correlations or patterns and things that we want to be able to address. So this is really a big win for us to be able to actually start collecting all of the data that we want to be able to look at in an easy to use way. So we moved in on day one. We had a target of 1.3. We started moving equipment in, and at the end of month one, we ran the numbers and found that we were at 2.8. Not bad. That was somewhere around where we were predicted to be, but when you just left the data center that was at a 2.0, it's not the best thing that you want to have on your reports. So we said, well, we'll wait another month and we'll see what happens. And it got worse. So next month we're at 3.2. So that started to bring some questions to light in terms of, well, who put the BMS system in, and how are these things being calculated, and how do we know that it's actually correct? As an analyst, Ray hired me to basically question everything, and that's my job, is to make sure that what we're looking at is accurate. So that sent us on a quest to figure out the accuracy of the PUE. And where do you begin with that? So the first place that we went to was, well, where is our PUE being calculated? And that's what this screen is a snapshot of. Is this our actual PUE calculation in the BMS system of how we can derive that value in real time? And that's constantly being monitored. Once we had that information, we could then take that and convert that into English so that we could now figure out what are the actual data points that we have being monitored. So take the calculation, figure out where all those parts are, and now from this point we could go to the actual environment and figure out, okay, these are the data points that we know we're monitoring, this is what was actually installed in the environment, let's see if it's correct. So we did a deep dive into the BMS system. We got up to speed very quickly on the power dashboards, the air handlers, the cup, basically learning everything that we could about the facility, because again, this was a 30-year investment for us. So the goal here was to really try and figure out, is our system properly calibrated for the next 30 years for us to be able to actually make, real improvements and not be fixing the wrong problems. So we decided to create a project to basically address this issue, and it was fully around analyzing the PUE and making sure that it's accurate as possible. Okay, and we chose Lean Six Sigma as our methodology to do that. Our company, we're a manufacturer, and we're a very big proponent of Lean Six Sigma. And that methodology really lends itself to documenting and managing the project across organizations. And we really wanted to get facilities involved with this because we knew at the end of the day, we could look at everything that we wanted to, but at the end of the day, facilities would be the one that would have to make changes to the system should we find anything. So we wanted to keep them involved and bring them to be on board so that they would be part of the process. So we went through the define phase and the measurement phase, and we collected all the data that we could. Again, 60,000 different data points. And during the analysis phase, we started immediately finding all different kinds of things. And this is a control chart that we put together, which really just exemplifies one of the tenets of the Green Grid's definition of calculating the PUE. And one of those is that you should not be collecting data samples while you're in maintenance mode. And that's exactly what we're looking at here. So we test our generators every Tuesday, and that can take them anywhere from 2 to 4 hours. And you can see that for that period of time, the PUE is literally in an out-of-control condition, okay? And those data sets are going to throw your numbers off. Now, this particular problem we're still trying to address within the BMS system because we want to build in a way for our facilities to be able to flag when they are going to do maintenance on the system, so that at that point we can still keep all the raw data, but we can also filter out maintenance mode as well, and that would also allow us to do tracking and trending of how much maintenance we do within the facility as well. So that's one of the projects that came out of this, was to actually implement some changes that the BMS system didn't do natively right from the start. So we consolidated all the different things that we found and put them together in a cause and effect diagram. And again, the goal of the project was to analyze the PUE and find all the different ways that something in the environment could impact the accuracy of the PUE. And there's basically 5 different categories there. We do live in a shared environment. It's not just a data center. We have about 150,000 square feet of lab space as well. We're tier 3, the lab space is tier 1. So there's a number of different challenges when you live in a shared space to figure out what your true numbers are. And that's what this was built around. The efficiency piece is actually numbers that would impact the bottom line. So anything in the green category would really pull power consumption money into effect, whereas the other buckets are really just reclassifying data on data center versus labs, kind of so forth. So another thing that we wanted to test was ESS mode. Again, in the UPS system, that's energy saver system. That's basically bypassing the double conversion process to go from AC to DC and back to AC again. And before we flipped that switch, because when we moved in, it wasn't enabled on the UPS system yet. So we said, well, let's take a look and let's chart the measurements and see what the actual impact is before we make that decision. And you can pretty clearly see when we flip the switch how much of an impact that has. You know, that dropped our mechanical KW almost about 160 KW, which translated to an impact on the PUE, dropping it from 1.7 roughly to a 1.4. So 0.3 of a point on your PUE was a pretty big number, and that really provided us the data that we needed to make a better decision. You know, so management can weigh the risk of ESS mode or not and say, you know what, the architect designed it in, this is the impact, let's go ahead and do that. So in the process of going through all of the PUE calculations, of the 60,000 plus data points that they're managing, we found that there was about 225 data points that actually impacted the PUE. And of those 225, we found 19 defects in the system as it was implemented. Okay, and so now we had to take that and go back to the architect, go back to the vendor that installed the BMS and our facilities and say, okay, so who's right? What do we need to do to get this more accurate? Because we're seeing differences on what it should be. So there's kind of a before and after snapshot of what our PUE calculation was and is today. The larger impact was actually on how we were calculating our mechanical KW. And there was some discrepancies involved, and basically the piece that was left out was the overhead of the Flywheel UPS system. So our UPS overhead was not being included in the mechanical KW. So we fixed those and improved the accuracy. And basically the net effect was our PUE calculation was off by about 7.5%, and that was because the mechanical KW is off by almost 24%. Okay, so in this particular case, unfortunately, it didn't make our PUE go down. Our PUE actually went up. But again, the goal was not to improve efficiency. The goal was to improve accuracy. Okay, so after going through this exercise, we were very, very pleased to find that, you know, we found some of the issues and we were able to correct those. Some of the things that come to light when you're doing constant monitoring of your PUE using some of the tools that we have is that you really get a good understanding of your environment. You know all the time what state your building is in, and you know what's normal for you, okay? And more importantly, you know when things are not normal. And this was a particular slide one morning. I happened to notice that our PUE went from a 1.4 to a 1.95. Started investigating and found that there was no reason why the building should be running at 1.95 at that time. So I went to the facilities and they looked into it. And one of the things they found was that we do a weekly rotation of our chillers. We've got 4 on site. We only need 2, and they rotate weekly. And one of them never shut off. So we actually had more chiller running than we needed. Nothing that would ever get alarmed on the facilities side. Again, they've got 60,000 points that they're monitoring for. They're not looking for something that's not broken. But from an efficiency standpoint, we didn't need to have that extra chiller running. Could have gone unnoticed for another week until the next time things were supposed to rotate. So again, being able to constantly look at things will help you to you know, find issues quicker and be a much more efficient facility. So in the end, we're really trying to do a comparison of moving out of Westboro, moving down to Durham. And you can kind of see that we've really made some significant improvements in building a new facility, where we went from a data center that was averaging a 2.0. We're very consistently hitting our 1.3 now, and we haven't even come close to the 1.5 megawatts. And we think that trend's going to continue as well. Our total annual power consumption, 48% of our power used to be spent in Westboro. And at this point, only 9% is down in Durham. So, you know, shutting off our Westboro facility 2 months ago was really a big win for us, because we've been able to save a lot. And the impact of the PUE, again, Durham is a very efficient facility, so the actual cost of making improvements at each decimal point is not nearly as much as an impact at our other facilities, such as Hopkinton or Westboro. But there's still advantages there, and we're going to pursue those as much as we can. So at the end of the day, over the past 2 years, we've you can kind of see where we've been headed with our trend, and some of the improvements that we've made, little things that we tweak here and there, and we've very consistently hit 1.2, 1.3 when we're in free air economization mode for our PUE. And the averages, we're hoping the average to get down below 1.3 sometime in the next year or so. Now I'll turn it over to Ray for CFD.
Great job. So like Joe said, right, I mean, part of his project wasn't really to drive down PUE, it was to get an accurate baseline. And I'll be honest, you know, when we rolled into the building and we noticed 3.2, 1.9, 1.7, we almost went into a frenzy, right? We're like, what can we do? Can we shut down an air handler? Can we shut down a flywheel? Let's raise the supply temperature. Let's do something to drive that PUE down. That was our natural reaction. And I think we can thank the Green Grid for that, right? Is noticing this and trying to drive some action. But what we had to do is we had to take a step back, and we had to say, well, hold on, we've been in the data center for a year. Let's look at what's happening from a thermal baseline. Let's dive deep into the data center to see what's going on. So the main part of that was running a CFD analysis. We engaged a third-party professional services team and went through a whole iteration of models and slides to show and get a good idea of what's going on in the data center. I could probably spend an hour just on this this project that we did, but I condensed it just to give you guys a good idea of how we set our baseline, and then just a couple things that we saw from predictive analysis and what we're focusing in on. So for us, the accuracy of the model was extremely important. We were shooting for 5% accuracy between the model and reality. So we used tons of readings. We took physical measurements. We took a lot of the data points from our BMS solution. A big part of this was leveraging our DCIM tool, understanding what type of devices were in the data center, how were they configured, how do they breathe, and where was their exact location. And then we had the benefit, since it's a new building, we had the benefit of leveraging the BIM model that the architects used to validate a lot of those measurements. Here's some of the parameters that we used. I won't go through all of them, but I think the most important parameter is that at the time that we did this model, we were only at about 25% of power capacity. We were running roughly about 528 kW. And our airflow was still rather high. We were still running at almost 100% capacity in CFM, which was around 290,000. So go through a couple of standard baselines that we calculated using the model. Basically, the first thing we wanted to look at was what was happening inside of our cabinets. How was the kW per cabinet? Granted, we were only a year into the building, so nothing stood out, nothing really crazy. I mean, most of our racks and cabs were empty, so that's where you'll see a lot of blue. Down on the bottom center, this is where our storage arrays are. Granted, they're pulling about 7.5 kW per rack. But then we noticed a couple red cabinets right here. We didn't realize at this point, at a 25% power capacity, why we would see upwards of 10 kW per cabinet. Happens to be this was our high density network region, so a lot of our networking equipment was stacked in those two cabinets. Gave us a visibility to go ahead and re-rack those and move them out to even out the load. Now, from an airflow perspective, the design of the building really showed true here. We have a consistent airflow, consistent CFM. What we did is we tested each individual perforated tile, and we saw about an average of 775 to 800 CFM per perforated tile, exactly what we wanted to see. But if you notice here, I mentioned cold aisle containment earlier, and we initially built the data center with 2 cold aisle containment solutions. And if you notice, the perforated tiles inside those containment solutions actually reduce the amount of CFM required inside those CAC units, roughly about 300, maybe 325 CFM, which was interesting to us. This really shed some light on our environment and our cold aisle solution. It's not a very great slide, but what I wanted to show in relation to CFM, static pressure as well remained very, very stable, very consistent throughout each perforated tile, and we did the same thing. We tested each perforated tile to get a reading of our static pressure. Now, the air handling units are based on static pressure, right? So the sensors talk back to the air handlers, and they try to maintain and continue to keep a constant static pressure. So this was really important for us. And again, it kind of validates the design was a good design for the building. Now this slide here, I'm showing 2 different things. This is our thermal baseline, and I'm showing what's happening inside the cabinet, and I'm showing what's happening inside the data center. So first off, you'll notice a lot of red cabinets, and this was extremely alarming to us. You're thinking, how, at 25% power capacity, how can we be intaking 95-degree air? Now, this doesn't mean that that's actually happening. What it means is that somewhere inside that cabinet, there's potential for 95-degree air. And what we found out is that this is primarily where all of our networking gear is, and some of our devices are side breathing devices. So in a hot and cold aisle design and layout, when you separate the hot and the cold aisle and you completely fill through with blanking panels your open spaces, you're basically starving those side breathing devices. And again, a real eye-opener for us to try to tackle that and to try to fix that before we did anything else. Now, from the room itself, what you'll notice is even at 25% capacity, here it looks okay. Here's our 2 cold aisle containments, perfect, stable 72-degree air, but we're starting to see a major issue here in our storage region. And something we actually tried to fix from our experiences in Westboro and Hopkinton actually bit us a little bit here. And what we saw in our other data centers was that as you start installing storage arrays and you butt them close to each other, you don't allow those storage arrays room to grow and for organic growth, extra demand. So what we did here is we actually left spaces in between our storage units for that growth that I was just talking about. Well, we weren't consistently separating the hot and the cold aisle, and that allowed a lot of our air to move, hot air to move into the cold aisle. And you'll actually see here, between rows 10 and 12, the cold aisle is almost non-existent. We're 78 degrees there. Great thing we did as part of that base, getting that base thermal modeling is now we can do predictive modeling. Now we can see, what's going to happen when we start to increase the load in the data center. So for this particular model, again, the parameters there on the bottom, 72 degrees set point, 5 air handlers running at full capacity, but now we've increased the load to 1.74 megawatt, which is roughly about 75%. We just didn't peanut butter spread the load throughout all the different cabinets. What we did is we already had an idea of what type of equipment we were provisioning, so we really put some thought around how we would provision another 1 megawatt into the data center. And now what you can see is even in our fixed cold aisles up here, even in our fixed cold aisles up here, we're starting to see a lot of hot air coming into the cold aisle. And then here in the storage area, it's just progressed and it's got effectively worse. But cold aisle containment has still remained at a consistent 72 to 74 degrees. So how can that happen? How have we seen this with the brand new design, brand new data center? One of the other things we changed from what we've learned in Westboro and Hopkinton was we made our cold and our hot aisles a little bit wider. We went from 4 feet to 6 feet. And this actually caused a problem for us. With the wider space and not having perforated tiles throughout that cold aisle, it gave that hot air the opportunity to come over the cabinets and right back into the center of the cold aisle. And you see that happening right here, basically everywhere you have a cold aisle, right? But again, really starting to validate the performance of a cold aisle. You see the cold aisle, now that we've maintained the integrity and we've sealed off the cold aisle, again, it remains at a constant 72 or 74 degrees. So what did we learn? First, again, in conjunction with what Joe was saying, we wanted to create an accurate baseline. Without that accurate baseline, you have no idea what changes you implement in the future if they're going to have a positive or negative effect. And more importantly is you have to understand your hardware. Getting that accurate baseline, it requires you to take a look at your hardware and understand how does it behave, how is it designed. We all know the data center is dynamic, and this proved this. You don't provision hardware inside a data center like you would fill a pool with water. You have pockets of high density, you have pockets of patch panels that will never get high density. You have open spaces. So you have to look at this as a dynamic environment. Having the ability to run predictive analysis was really key for us, right? Again, that baseline and then having the ability to see, this is what I plan to do in the next year, how is that going to affect my data center and the environmentals within my data center. And then lastly for us, we want to revisit change. We want to make sure that we're constantly going back, revisiting this. So as an EMC program, we'll be doing CFD analysis every year to ensure that we're going to rerun our baseline and then give us the ability to rerun some predictive analysis. One of the biggest things that we saw was the benefits of cold aisle containment in our design, right? And you can argue hot aisle, cold aisle, exhaust, but for our building, for our design, the architecture firm, when they were designing it, they looked at all 3 types of containment. And for us, given the design of the building, it was cold aisle containment that was going to give us the most efficiency. So today we have 2 types of cold aisle containment units. We have one that's a standard cold aisle that has fixed cabinets. So that supports hardware installation at the RU level. So your basic server, storage device, network devices. But as we saw in the modeling, our storage area was the main problem. It was the biggest problem. So we wanted to develop a flexible or hybrid cold out containment that allowed us to support installations at the cabinet, at the rack level. So with this new solution, we can roll in a full array, break down a panel, install the rack, quickly seal it up, and maintain the integrity of the cold aisle within about 20 to 30 minutes. And this is one of the predictive models that we ran as part of our CFD analysis. Parameters, again, very, very similar, 72 degrees, air handlers at full capacity, 1.7 megawatt load, but now we modeled 100% containment. You see the room is getting hot, it's upwards of 89, 90 degrees, but the cold aisle containment still stay within 72 to 74. So basically what we're doing now is we're driving towards 100% containment. And because of that, we recently installed 5 new containment solutions. So we had a great opportunity when we sealed these cold out containments up, to look at some of the metrics that are really important to us, some of the data points that Joe uses for the widget, that Joe uses as part of his PUE analysis. So we took 4 primary data points: total CFM, air handler KW, cold out containment, and hot aisle. It says HAC, but it should be hot aisle temperature, and then return temperature at the air handler. So I'm going to quickly go through our trending of those data points to see how they reacted when we sealed up the cold out containment. First thing we looked at was total CFM. So that gray box there, that is from the time we started sealing the 5 cold out containments and roughly about the time we finished. Immediately you can see our total CFM requirement dropped. It dropped about almost 16,000 CFM from about 277,000 to roughly 261,000 CFM. So good news there, moving in the right direction. CFM, air handlers, obviously they're direct correlation there, so you almost saw the exact same trend on our air handlers and the power to run those air handlers. And the net result there was a 15% reduction in KW per air handler. This is one of my favorite slides. We do as much as we can to improve efficiencies, but in data center operations, my main concern is the stability of the environment, providing the right temperature to my IT hardware. So this is a view inside one of our cold out containments. We had 8 different sensors inside that cold out containment at different heights, at different areas inside the CAC. And what you can see is before we sealed up the cold out containment is that our temperatures were ranging from 72 to 77. So really a 5% or a 5-degree difference in those sensors. Now, as soon as we sealed off the cold out containment, you can see all of those sensors and all the temperature ranges really start to come down. The net result was a reduction in almost 2 degrees, but now instead of having a 5-degree delta, it's down to a 1-degree delta. Those sensors are now running at 72 to 73 degrees. Again, something we really expected to see and we're very happy to see. One of the things that we didn't expect, but there's a reason for it, is that our hot aisle actually went down. The temperature in our hot aisle actually went down almost 4.5 or over 4.5 degrees. How can that be? We completely expected the hot aisle to go up. But since we're not containing our hot aisles, we actually put our sensors on the back of the devices. So this is really an exhaust temperature, not a hot aisle temperature. It's not an average hot aisle temperature. So with the cold aisle going down, the delta T of the device isn't changing, so that is reflected in the exhaust actually going down as well. So it made more sense. It was a little intriguing at first, but it made sense once we started to dive down and figure out where the sensors were located. And then lastly, what we did expect to see is we expected to see the return air temperature at the air handler unit go up. Didn't go up as much as we thought. It went up almost half a degree, but at least it's moving in the right direction. So some of the things we learned here is, cold aisle containment, it really helps create a stable supply of cold air to your devices. I didn't show the trend on static pressure. I mentioned how important static pressure was for us, and what we saw is that the system was pretty intelligent. Once we sealed off those cold aisle containment units, it was able to stabilize the static pressure and ensure that only the right amount of CFM was being supplied to the cold aisles. And then lastly, the cold out containment obviously has a real positive impact to the data center and to the environmentals that are supporting your IT hardware. All right, and then lastly, Joe will cover some of the things we're doing today, leveraging DCMM to continue to drive IT efficiencies.
Excellent. So a number of the projects that came out of analyzing the PUE, one of them was just raising the supply temperature in the data center. Everyone wants to get it as hot as you can. ASHRAE raised the specs. They're up to 80.6. So we kind of chose 78 as the number. That's our target goal for what we'd like to get to. And we started looking at, okay, so what would that actually mean in our environment? Right now, based on the historical weather patterns in North Carolina, at 72 degrees, we can enter free cooling about 57% of the year. If we get up to 78, that would translate to about 81% of the year. So it's a pretty big amount of usage that we could get. However, the electrical savings aren't as great as we would like them to, and a big portion of that is because we do have our cup is actually shared with the lab space, so our percentage of that isn't as great, but the translates to about 15K per year, but it's something that we're looking at getting into anyway. Airflow optimization. So there's been a lot of talk about that. Again, when we went into the data center, it was built at 100%, so we were putting in about 300,000 CFM to an area that didn't have much equipment into it yet. So one of the first things that immediately hit us was, well, why don't we look at taking some of those perforated tiles out until we actually need them and start going to an airflow on demand type of model. So we did a test and we removed 14 perforated tiles in a row that had no equipment, plugged up the holes and took some readings. And we saw on average each air handler dropped about 2,500 CFM. Okay, so about 5% drop on each air handler, and the power associated with that went down about 11%. So, and that was just for 14 tiles. And in looking through after the CFD analysis on the data center, we identified probably close to about 100 tiles that we can do that to. So again, moving into a large facility that's been built out, not the most efficient. So we're trying to clean that up and get to more of an on-demand type of style. Side breathers, another issue that Ray talked about. This is just kind of showing you, we have a thermal imaging camera that we do thermal audits with. And if you just looked at the front of the rack, you would think that everything was okay on that, but it's not until you actually get into the CFD of the device and you can actually look, and that's what was called out on that slide that Ray showed. And you're actually looking at this device here, which is predicted about 113 degree inlet temperature. Okay, so these are the devices that we need to get some baffles for, and we need to figure out better solutions for how to get air to those in a cold aisle, hot aisle environment. One last plug is in the cold aisles, seal everything. So these are pictures that you can see where we're looking at our equipment and just trying to go through and find where all the cracks are so we can get the best use of the airflow as possible. So the last piece I wanted to cover is WUE. We felt pretty confident that our PUE was being taken care of. So we went to the next metric in the XUE tool set, and that's water. Unfortunately, our building was not designed with water in mind for measurement, so that's not in the BMS system at this point. But we do have water meters throughout the building, so it was just a matter of us taking on and going through that to find out if I could figure out how to calculate that number. So we have two subsystems in the building. One of them is for humidification and one is for cooling towers. So those were the gallon counts that we had, and we were able to pull back some data from that. And this is what the WUE translated to. So we figured out the data and immediately went and said, okay, great, so is this good or bad? Well, there's not a lot of data out there for us to find. But one of the first things I went to look for was, okay, well, that's what our meters say. Let's start applying a cost to this. So let's go get the water bill and see if it lines up. And we immediately realized that it did not. And the city was actually counting a lot less gallons. This was one of our wins than what we were being charged for. So again, you need to benchmark the environment to figure out what is actually correct. And in this particular case, our water meters, they can be set to send out a pulse either at 10 gallons or 100 or 1,000. And these were off by literally a factor of 10. Okay, so they weren't, the electronic reporting of those weren't in sync with what the gallon counters were showing and so forth. So again, 60,000 data points being configured in 9 months. If you start looking into things, you will find things that are misconfigured. And that's really what we've been trying to do, is really make sure that we have a solid environment going forward for the next 30 years. Just to wrap it up, some of the things that we're doing next is we're doing a deep dive on the WUE. We'll be taking on carbon, and then once we've done the outside of the data center, we're going to start looking inside the data center with a lot of things you've already heard about today with going inside the server storage, things like that, and getting to 100% cold out containment. So there's not much time left for questions, but Ray and I will be here. We'd be happy to take questions up front or out in the hallway.
Any questions? Give a couple. She said 2.
You mentioned that you were harvesting the water from the rain. How did you incorporate that in your WUE calculation?
Well, today the water that we harvest, it all comes from the roof, and it all goes to non-potable demand for the building, right? So it's really for the toilet, the water closets. We have been looking at and considering creating a bigger tank, building a bigger tank so we can start using that maybe for some water recapture for the cup. We're also really close to Durham's water reclamation facility, so we're looking at things like that too. But today it's very minimal. It's the first time we've ever done that. So our tanks are roughly in our first phase of the building, it's 1,600 gallons, and then in the second phase it's 2,500 gallons. You saw how much water we're using. There's no way those tanks would supply or help us support the data center.
Very good presentation. I want to ask you a couple of questions that are slightly outside the scope of your presentation. Anytime that somebody does a new data center, I'm curious about these. First was a risk assessment that you did and determined that you wanted to go with a rotary system versus a static system. And I was curious about the thought process that led you to that.
Risk assessment for what type of system? I'm sorry.
On your UPS system, you went with a flywheel system as opposed to, say, a static system. So I'm just curious, when you did your risk assessment, you figured out that that was the right thing to do, cost, benefit, and all of that. But I was curious what route you followed to get to that conclusion.
Well, I guess I can say this. I'm going to expose some dirty laundry here, but really our only outages before this facility were primarily due to, our major outages, I should say, were due to batteries. Up in the Northeast, storm systems, we've had a couple instances where, the batteries are discharging over a period of a few hours, and we got hit in 2008. So when we started really looking at options, we looked at Flywheel, and it's been for us in the last 2 years. We've actually have leveraged the Flywheel once, and it worked flawlessly. So.
Yeah, for us, it was all about the recharge time. So the flywheels can get back to 100% capacity within minutes, as opposed to hours or longer with the batteries. And
okay, thank you.
Once you're hit by something once, we're not going to let that happen again.
And then another question I'd always like to ask is, what surprises did you get when the inspectors came through? Fire inspector, fire marshal, electrical inspector, mechanical inspector, whoever.
It was beyond my scope. Yeah, it wasn't. Probably a question more for our facility and the architecture team.
Okay, thank you.
Sorry.
What was the reason you went with a cold aisle containment rather than the hot aisle containment? And also, did you consider using a dynamic cooling management system like Vigilant or SynapSense? And if you, obviously you're not using it, so why not?
Yeah, so the architecture firm, I mean, they looked at various solutions, right? And they ran their own CFD analysis. But the design of the building, the way we run with a 3-foot plenum in the subfloor, our air handlers are, with air economization, it just, through their modeling, cold aisle containment seemed to provide the most efficient. Granted, yeah, in different facilities, different data centers, I'm sure hot aisle containment, will be more efficient, and there's other technologies out there, other designs that would be just as efficient. But for our building, it was
based
cold.
on the modeling, they just couldn't get that amount of power into the size room that we had unless it was specifically cold aisle containment. So.
I'm not sure if the architecture firm actually looked at that, but I know that they did look at quite a few different solutions. With any dynamic cooling, no. It's something that we've been looking at in the next couple of years, but no, right now there's no dynamic, so it doesn't react to what's actually happening inside the data center. I'm sorry, I misunderstood your question. Okay. Thank you very much.
All right. Thank you.
Enjoy the rest of your day.
So the next session in this room will be the IT recycling metric. The current and short-term projected state of EOCOC will be held in track 2.